Hello, everybody. So I want to talk today about continuous delivery. I'm going to start by sharing my screen so that you'll be able to see my presentation, which hopefully you can see something now, but that's not the right thing. So now you should be able to see my presentation.
Yes, that's correct.
Good. Thank you. So I think that we talk in our industry about change a lot. We talk about software being an industry of change. And that's certainly true. But I think that there are different classes of change. There are different categories. And I believe, I think that an awful lot of the change that we think about is kind of like froth on the top of the ocean. It's not this big stuff that really modifies the way that we think about or practice software development. Periodically, a change like that does come along, though, and there have been some big ones. The move to higher level languages, the introduction of object orientation, graphical operating systems, the web and the internet. These are massive changes that really had a big change in the way that we thought about and approached software development. I believe that continuous delivery is one of those kinds of changes. And what I hope to do with my talk today is to convince you that there might be something in that I might not be just being self-serving and trying to sell you a book, that there's more to it than that. So let's begin by looking at the state of software development in our industry. And this is kind of old data. This particular one's going back to 2010. But these sorts of surveys of software projects have been carried out in our industry for decades. And most of them are not scientifically rigorous. These are not taking a careful look at they don't have a control group. They're not looking at statistically balancing the information. They're not analyzing it in a scientifically rigorous form. But nevertheless, over those decades, the story that these sorts of surveys of the software industry tell us is that there's something wrong. In this last one, if you're a fan of Schadenfreude, taking pleasure in the misery of other people, then this one's kind of an amusing, in a sad kind of way. In a study of nearly 6,000 large-scale projects, 17% of the projects went so badly that they threatened the existence of the company performing the project. That's not a history of success. That's a problem. That software has is that risky. We could think about it in a different way. If software projects were normal things, there would be a normal distribution of software project success, as many software projects would finish ahead of schedule, under budget, delighting their users, as finish behind schedule, over budget, and annoying their users. But I don't think that's what we think of as normal. I think that what we tend to think of as normal in software projects is more like the red curve here. And we tend to be weighted towards the failure end of the distribution. And I think that says a couple of things. First, I think it means that we start off new software projects being very nervous and very scared, and we try to overcompensate by thinking harder and analyzing more deeply in order to mitigate the risks. But I think it says something more profound than that. I think that what it really says is that we've got the model wrong. If I'm going to say the same words again, if software projects were normal things, there'd be a normal distribution. The fact that there isn't a normal distribution says that there's something wrong with the model and the way that we're approaching software development. And that brings us into this. This is a little GIF animation that I'm very fond of. I like this animation, and I like it for a variety of reasons. I am something of a popular science nerd, and one of my hobbies is reading about physics. And this is kind of going back to the dawn of physics. So that's one reason why I like it. But I also like it is because this is a lovely visually impactful presentation of the importance of a paradigm shift. And I think that's what we're talking about. On the right-hand side in this diagram is the geocentric orbit of the planet. The orbits of the planets is in both of these pictures, but on the right-hand side, based on the geocentric model of the solar system, and on the left-hand side, the heliocentric view of the solar system. The picture on the right-hand side is the model that humanity held for the way that the universe worked for probably hundreds of thousands of years, certainly tens of thousands of years. And in that model, the assumption is that we make is the obvious one, that we are at the center of everything, because clearly we're stood still here. And when we look up at the sky, what we can see is everything is going around us. And that's true of the sun and the moon and the stars. And then there are the planets. And the planets don't obey that rule. The planets do something else entirely. If we are stood still, the planets are really very hard to explain. In fact, the name planet that in English we use to describe these bodies in our solar system is derived from an ancient Greek word that means wanderer, because of what we're seeing. If you imagine standing on the blue dot in this picture and looking at one of the red dots, what you're going to see is that sometimes that thing goes backwards in the sky. It's really, really quite confusing. During this course in human history, some of the most complicated devices that we built were built to try and predict the orbits of the planets, a clockwork thing called orreries that would try and figure out where on Earth the planets would be on any given date. It takes a shift. It takes a shift in perspective, a shift in mental gears to be able to understand what's really going on here. And in this case, Copernicus and Galileo came along and they said, no, it's not us that's at the center of the universe, it's the sun. That's wrong, but it's more accurate. And certainly when we're starting to look at the planets, it's accurate enough. Now, it's kind of obvious what's going on. If we place the sun at the center of the solar system, then we can make predictions about where the planets will be. Even I could do the maths that would be able to figure out where the planets are in that kind of model. Now, if you were to inhabit the solar system on the right-hand side of this picture, you wouldn't be able to, Newton wouldn't be able to come along and come up with an inverse square law. A few centuries later, Einstein would not be able to come along and come up with bendy sheets of space-time and general relativity. These are kind of fundamentals to our understanding of the way that physics and the cosmos works. And we wouldn't be able to get there in that model without making this shift. I think that, so why on earth am I talking about the orbits of the planets in a talk about software development? Because I think this is a good analogy for where the software industry is. I think that an awful lot of our industry is inhabiting, in essence, the solar system on the right-hand side. We're looking at it we're looking at software development in the wrong way. We're approaching it incorrectly. And as a result, we're forced to add complexity on top of complexity in order to cope with this misjudged model of what's going on. If we can get down to a simpler model, a more accurate model of what software development really is, we can get a fundamental and significant change in both our approach, but also the efficiency, the results that we get from software development. And that's mostly what the rest of my talk is about. So where are we? Going back to where we are as an industry, I would argue that the state of software development has kind of been less than optimal. But I would also argue that there are signs of change, that there is hope, and that actually this is a problem that we now know how to solve. Everybody's not solving it in the ways that work, but we know what works now. And I'm going to come back to that and explain what I mean. But I did choose this picture with some care. This is clearly better than the previous picture because the bike has round wheels rather than triangular wheels. But also this is not a mass-produced product. This has been tailored and designed and made in somebody's shed. But it is a bike with a jet engine attached. And I think that's the kind of thing that we're talking about. So again, looking at the history of our industry, what have we tried? Well, we've tried to look at other industries, and we've tried to adopt what we've learned from other industries and apply them to software. One of the big mistakes that we have made in that is completely understandable, but much of human history, nearly all of human history, is based on in production of things, in producing physical things. I have here a cup in front of me, and looking at this cup, the design of this cup is kind of interesting, and the way in which we're going to come up with that is going to be a thoughtful process and so on. But the really hard part of trying to produce cups like this is to scale out the production of these so that we can produce them at a reliable level of quality, at a reasonable price, have all of the materials arrive at the right time, and all of that kind of thing. Production in the physical world is a complex and difficult thing, and as a result, we tend to always think about production problems. In software, we never have production problems, because if I make a software system, no matter how big or how complicated, once I've designed it, once I've developed the system, I'm kind of lumping in the development activity as a design activity, because I think profoundly that's what it is. So once we've kind of created the design of the system, producing it is essentially free. Once I've got a sequence of bytes that represent a system, I can clone that sequence of bytes almost infinitely for next to zero cost. And so our problem in software development is never one of production. And that's one of the profound mistakes that we have made in our industry over decades now. So we've tried to apply production line style thinking to software development, and we tried to, and it's natural that we did so, but it was a big mistake. So we've come up with waterfall methods that are the software equivalent of a production line. We've come up with V models, and we've come up with breaking problems into small pieces and building, as a result, siloed organization where we throw change over walls between different groups of people and lost information and efficiency as a result. We've tried to evolve this over time. We found that those things didn't work, and we started applying more iterative approaches to development. And this is a picture of the Rationale unified process from the late 90s. And then we started thinking in agile terms and applying more agile thinking to project management. Scrum is a very good agile project management technique, but doesn't really say anything about engineering. So we added some of the engineering stuff with techniques like extreme programming. We've tried hiring really smart people and putting them in a corner somewhere. And we've tried hiring young smart people because they're a little cheaper. And we've tried hiring young smart people in foreign countries because they're a little cheaper too. This has had an impact on the industry, but it hasn't had the impact that we wanted. It hasn't solved the problem of how do we build better software faster. Looking at the history of software development, this is an interesting document. This is a document that kind of concreted that idea of production line thinking in software development. This is the document that introduced for the first time the concept of waterfall processes to software development. This document was written as a contribution to a conference held by the standards body, the IEEE, in 1970, and was written by Dr. Winston Royce. The document is interesting. You can download it off the internet and have a look at it. It's about 15 pages long in this format, and this diagram, which is famous, which nearly everybody will have seen a version of, is on page 2. And what happened is, you can imagine in 1970 being a busy software developer or involved in software development, flipping through the paper and getting to page 2 and seeing this big diagram and saying, oh yeah, I understand what he's talking about, and then not reading the rest of the paper. Going back to your team and writing on the 1970s version of a whiteboard and saying, here you go, this is what we're going to do. And that's a big mistake, because that's not what the document said. What the document said was something else entirely. The next paragraph I've exploded and highlighted so that you can read. The implementation described above is risky and invites failure. The testing phase, which occurs at the end of the development cycle, is the first event for which timing, storage, input-output transfers, etc., are experienced as distinguished from analysed. These phenomena are not precisely analysable. So the paper that introduced the concept of waterfall to our industry was saying, whatever you do, don't do waterfall. That would be dumb. But that's not what happened. What happened was that we did do waterfall, and we did it a lot. Most big organizations with any legacy are still infected with this idea, even if you are working in agile teams. If you're working in an agile team in a large organization, my bet is that the large organization is probably organized around waterfall thinking and principles. You'll be doing long-range planning. You'll be doing budgeting for teams over months or years sometimes. All of those kinds of things. That's just production line thinking. It's waterfall thinking. This is the diagram that Dr. Royce was actually recommending. The way that the document is organized is that he incrementally builds up this diagram until he ends up with something with this. And I concede that this is not as obviously appealing as the first diagram. It's a lot more confusing, but it says some interesting things. It says, involve the customer, do the job twice if possible. Testing must be planned, controlled, and monitored. You should concretely establish feedback loops from testing into software design and from software design into the requirements process. I think if we were to look at this with the benefit of 21st century hindsight, we'd probably call this an agile process because it's iterative, it's feedback driven, and it's about learning. And that's really what's important. So just to kind of break this up a little bit, here's a series of little pictures to demonstrate what's been going on for a while in our industry. In this case, by analogy, in this case, there's something unpleasant has happened. A car has fallen off a quayside into the water. What do we do under these circumstances? Well, we rent a crane and we try and pick the car out. Oops, what do we do now? If you guessed bigger crane, well done. Can you see where this is going? Yeah. Einstein defined insanity as doing the same thing over and over again and expecting different results. So if our software development process is not doing exactly what we want it to do, we should try something else. We shouldn't just keep banging our head against the wall, doing the same old thing and expecting it to be different. I think a good starting point for that is here. I think that any organization that produces software for any purpose fundamentally wants this. They want to be able to have an idea. They want to be able to get that idea in the form of working, useful software into the hands of their customers. And they want to be able to learn from that. They want to be able to gather feedback so that they can understand whether it was a good idea or a bad idea or what they should do next. And I think that's a great starting point. So if we were to work to just optimize for that, we'd be doing quite well, I think. So I want to pose a question. What's the most successful invention in human history? And here are some pictures that are intended to mislead you. You could I'm sure there are things that are going through your heads. You're probably thinking about wheels and fire and stuff like that. And if you're thinking a little bit more philosophically, maybe you're thinking about language or maths. I would argue that all of those things, while some of them are fantastic, I would argue that the most important invention is this. For the vast majority of human history, we lived essentially a non-technical existence. We had agrarian societies. The wheel is only about 7,000 years old. So for 200,000 years, we couldn't even make wheels. So we lived in hunter-gatherer groups. Agriculture is about 10,000 years ago. But for all of that time, if you kind of plotted human progress in terms of the knowledge that we gained, then on any non-logarithmic scale, if you include up to the present day, it's a flat line. And then about 300 or 400 years ago, that flat line starts to tick up, and then it grows exponentially through the 20th and 21st century. And that is as a result of the Enlightenment, the application of scientific reasoning, and specifically the application of scientific reasoning to solving practical problems, which is what we call engineering. And by science, I don't mean space shuttles and large hadron colliders. I really mean this. This is the scientific method. This is the simple four-step process that we invented only a few hundred years ago, but has completely revolutionized the societies in which we live and enabled all of the high-tech civilization that we now inhabit. So the scientific method, this is Wikipedia's version. We make a guess based on experience and observation. We propose an explanation for what we observe. We make a prediction based on the explanation, and then we test the prediction with an experiment. That's it. That's the difference between living in a cave or in a mud hut and having an iPhone. That's the difference. It's applying this kind of thinking to solving practical problems. I would argue that software is one of the more difficult things that we as a species undertake. Software is weird. It's strange stuff. We build the most complicated systems that humans create in the form of software systems. A Boeing jet has something like somewhere in the low millions, maybe a 10 million, maybe 12 million pieces. How many lines of code does a big software system have? A Volvo truck has 80 million lines of code in it. So we're talking about stuff on a different scale of complexity, and yet we don't often apply this kind of thinking to the way in which we approach software development. And when we do, we get remarkable results. So what are we really talking about here? We're talking about, this is a model I like to use, which is kind of based on this, starting to think about this and starting what could we do to get more deterministic in the way that we work? How could we measure more effectively? And the building block of that is feedback. And so we want to establish fast, efficient, high quality feedback loops so that we're able to learn more quickly and more effectively. And we might be learning that our idea is good, or we might be learning that it's bad, but we're going to learn and we're going to focus on learning. At the outside of this feedback loop is the loop that I've already mentioned, the one that software development is really foundationally grounded in, the idea from idea to useful software in the hands of our users and learning from that. At the inside is the fast, high-speed loop of test-driven development so that we can validate that our code is doing what we think it is. And in between is the use of executable specifications and other forms of acceptance tests to verify that the software is deployable, configured correctly, doing what users want, fast enough, secure enough, all of those sorts of things. As you can probably tell from my talk so far, I'm a popular science nerd, and this is if you're interested in physics at all, you'll know who Richard Feynman is, a first-class genius, one of the finest minds that our species has created in its history, and also fantastically quotable on the topic of science. And this is one of Feynman's great quotes: "It doesn't matter how intelligent you are, if you guess and that guess can't be backed by experimental evidence, then it's still just a guess." So we should be trying to figure out how to move beyond guesswork and into the realm of experimentation. How can we try out our ideas? How can we validate that they're correct? And if we start thinking about experimentation, then we start thinking about measurement and controlling the variables and those sorts of ideas. I think that's pretty good stuff. And if we were to stop now and you were to take my advice and just start applying that kind of scientific thinking to your day-to-day work, then I think that you would see an improvement. But you'll be pleased to hear, because we've still got more time to go, that there's more to it than that. The next thing to think about is, so what are we going to use that experimental capacity to do? It's hard to figure out what to measure. And one of the great tools that we can use is cycle time. Cycle time is a measure of the efficiency of our development process. The idea of cycle time is how long does it take you to go from idea to something that somebody can use? And the way that you measure it is, imagine for a moment a single line change to your system in production. And imagine that change going through all of the steps that it should go through in your normal development process. Somebody's going to identify that this is a good idea, and they're going to prioritize it appropriately. Somebody's going to capture that in a requirement of some form. Somebody's going to allocate that to a team. The team's going to pick it up. They're going to decide how they're going to design software to fulfill that need. They're going to write some tests. They're going to write some code. They're going to deploy it, and so on and so on and so on, until it's in the hands of users delivering value. So the reason that we choose a single line change is that we're trying to take out how long it takes you to do work from measuring the efficiency of your process. You can, if you're scientific in background, you can think of this as kind of a die trace analysis of your development process. I'm going to show you two cycle times. This first one that's been on the screen for a couple of minutes is based on an order management system for a large bank. In that bank, if they followed their own development processes, they couldn't make a single line change to their production system in under 103 days. If it takes you 103 days to make even a simple change, your development process is slow, inefficient, and you don't essentially have a feedback cycle at all. Because if somebody comes to me 103 days later and says, Dave, you've just broken production, I have no clue what I was doing 103 days ago. And even if I know what I was doing, if I can look that up, I'm not going to remember all of the detail, all the nuance that's going to help me fix it. I might as well be coming back to this problem for the first time. So I'm going to have to learn. It's going to be slow for me to figure out what's going on. The other thing that's going to be true is that if I can only get stuff into production once every 103 days, that means that what's being dumped into production is a massive pile of changes. And so my change is going to be immersed in a whole bunch of other changes. And maybe the problem is my change, or maybe it's your change, or maybe it's somebody else's changes. And we're going to have to figure that out too. So there's a big cost to being this slow. The risk of all that big pile of changes is huge. So there's also a big risk to being that slow. The alternative is this. This is the cycle time for another real project that I worked on. I was involved. I had the very good fortune to be involved in one of those kind of career-defining projects. I was hired at the beginning of a startup to create one of the world's highest performance financial exchanges. In terms of scale, the project on the bottom of this slide, the project represented there was about 15 to 20 times larger and more complicated than the project on the top. But we could make any change to the entire enterprise system that represented that software, and we could get a definitive answer back, is with no more work to do, is it releasable? And we could get that answer back in 57 minutes. That is just a different thing. That is like the shift from the weird geocentric orbits of the planets to the heliocentric model. It just simplifies everything. It's radical in terms of its impact. If I can get an answer, a definitive answer, can I release this back in 57 minutes? Then it means that I can try ideas out quickly and efficiently. I can give you a one example of that. At one point in the history of this project, we decided that we didn't like the commercial terms that we had with our relational database vendor for a very large, quite complex data warehouse. So we decided that we would try something else and see how much work it would be to do that. So we downloaded an open source relational database package off the web, and then we scripted its deployment. We put it into our repository for those kinds of infrastructure artifacts. We scripted the deployment of it. We put that change into our deployment pipeline. We waited 57 minutes and a couple of tests failed. So we looked into the tests, we figured out what had gone wrong, we corrected the problem, we resubmitted the change with the fix. It went through the deployment pipeline, all of the tests passed, and the next time we went into production, we did so with the new version of the relational database system. Now, the entire story that I've just told you took half a day. It took a morning. It took 2 people working for a morning to achieve that. I've worked places where that would have been impossible to kind of think about, but I've worked places where even if you could think about it and you could do it, it would take you months. It would take a team of people months to achieve that kind of change. And that's the kind of impact that this fast cycle time can give you. It gives you the opportunity to try these sorts of ideas out and see what happens. I think that if we were to stop now in this presentation and you were just to take me seriously in the things that I said, you decided that what you were going to do was that you're going to work to reduce your cycle time incrementally, step by step, through a series of experiments. You were going to validate what really worked and what really didn't as you went through that process. I think as a result of that, you drive out all of agile thinking, all of lean thinking, all of DevOps thinking, and all of continuous delivery thinking. You can't have a 57-minute cycle time if your teams are too big, because the communication overhead will slow you down too much. You can't have a 57-minute cycle time if you have siloed teams, because the handovers will slow you down too much. You can't have a 57-minute cycle time if you don't have a great story on automated testing, configuration management, infrastructure as code, automated deployment. You've got to have a good architecture. All of these things tend to play out as a result of driving down the cycle time, which means that we can use experimenting to drive the cycle time to start to drive better behaviors. One of the reasons why continuous delivery has become the aspirational goal for most software companies these days is because it allows you to really get to the value that Agile promised through this technical path. It's a tool that you can use to drive you in the direction of just better behaviors across the board. So what is it that we're really talking about? The phrase continuous delivery comes from the Agile Manifesto, which says that our highest priority is to satisfy the customer through the early and continuous delivery of valuable software. It's the logical extension of continuous integration. It's a holistic approach to development. A good mental model is that every time that we commit a change, we give birth to a release candidate, and our job from then on is to prove that that release candidate is not fit to make it into production. That might sound backwards, but that's another one of those ideas that we can steal from science. This is the idea of falsifiability. I can never have enough tests to prove to you that my software is good. But as soon as I have one test that fails, I know that my software is not good enough, and therefore I can reject the change. This is falsifiability, and the classic example is I can never prove to you that all swans are white, but if I see one black swan, I know that they're not. We're trying to create a repeatable, reliable process for releasing software, which means that we need to automate pretty much everything. That means we've got to keep pretty much everything under version control. We've got to treat quality seriously. We want to do things more frequently so we can identify problems more easily and we can fix them. We're going to treat done, our definition of done is in the hands of users delivering value, and we're going to aim to improve continuously in this process. This is a quote from a long time ago now, but if agile software development was the opening act to a great performance, continuous delivery is the headliner. I think it's not a boast to say that continuous delivery as an approach to software development is what we state of the art in our industry. It's what the best software companies in the world tend to do. Fundamentally, what we're looking to achieve is one of the tools that we're looking to achieve this fast feedback, this clarity, this engineering approach is this. This is the idea of a deployment pipeline. The deployment pipeline is our falsification mechanism. A deployment pipeline goes from commit to releasable thing And within the scope of the deployment pipeline is everything that it takes to achieve releasability. We're going to get fast development-led feedback in our commit stage. We're looking for feedback in under 5 minutes that our change is good. And if those tests pass, everything else is going to be fine. And that's kind of very developer-centered. Does the code do what I, as a developer, want the code to do? Then we're going to evaluate it from in other contexts. Does it do what the users want to do? And that's where we do acceptance tests, creating executable specifications for the behavior of our system. Performance tests, security tests, data migration tests, whatever it takes to achieve a releasable outcome. This is a fantastic tool too for regulated organizations, because imagine for a moment trying to build a machine like this. It's almost impossible to even imagine building a machine like this where you don't have complete end-to-end traceability of every change that goes to production. The deployment pipeline is that route to production. Around this kind of time, when I'm talking to people about this kind of stuff, I start to get some people saying, yes, but. And one of the yes, buts is, okay, so this might work for small projects, but it can't possibly scale. My answer to that is Google. Google have taken the somewhat unusual approach to putting the vast majority of their software in a single monolithic repository. They build and test logically everything on every commit. They run millions of builds a year, and that number is growing exponentially. They actually have more than hundreds, and this data is a bit out of date. They now have billions of lines of code, and they run tests all of the time. So if your problem is bigger than Google, then maybe it doesn't scale. But so far, the data is on my side. It scales pretty well. The next pushback is, this is slightly confusing the idea of continuous deployment with continuous delivery. Continuous delivery is working so that your software is always in a releasable state. Continuous deployment is saying, if all of the automation is good, we're just going to push the change on an automated basis into production. That's great for some industries and is probably a bad idea for others. But for those industries where it is great, it really is great. So releasing all the time is a recipe for disaster? Well, releasing all the time is actually the safest way to do things. Amazon, on average, release a change into production once every 11.6 seconds. On average, every 11.6 seconds, one of those changes goes to 10,000 servers. Since they've been doing this, they've seen a dramatic reduction in timeouts due to defects being introduced into production and outages caused by rollouts of change. Think about it for a minute. If you're pushing change frequently in small steps, if you have the capability without bringing the system down or being able to push a change into production every 11.6 seconds, what that means is that's going to encourage you to work in those smaller steps. Each step is going to be simpler and therefore less risky. There are fewer chances that you're going to mess something up. And if you do mess something up, it's going to be easy to roll back. And that's exactly what the data from Amazon says. I sometimes get the pushback, okay, I'm sure it's great for simple software like Google and Amazon, but my technology is more complicated than that. And the example for that is kind of, what about if there's hardware? Well, a good example is the HP LaserJet firmware team experience. And what they did was that they captured a kind of before and after picture. So before, they were in a mess. 5% of their global development effort, a team of nearly 500 people, went on creating new features. They spent an awful lot of time doing other things. After they adopted continuous delivery, 8 times as much effort went into new features. They spent a lot of time writing tests, doing continuous integration, automated testing, improving tools. All of that stuff is extra, but that's an investment in efficiency. This is captured in this book, and overall the development costs went down while the capacity went up, and so on. It's a dramatic, orders of magnitude improvement in some cases. The impact of continuous delivery, this engineering-led approach, is quite dramatic and is often, in many kinds of measures, significant. 8,000 times more deployment, 44% more time on new features is spent by continuous delivery times. That's a nearly 50% improvement in the efficiency with which we're delivering software. And the bottom line is the bottom line. Organizations that practice continuous delivery and its associated behaviors make more money than organizations that don't. They make more money, they produce better software faster, and the people that are building the software have more fun and report a better work-life balance overall. So there's quite a lot going for this. What sorts of organizations practice continuous delivery? This is my wrap-up slide. And I think it's many of the organizations that you would think of: Google, Amazon, Stack Overflow, but also some organizations that might be more surprising. The Department of Defense in the United States are using continuous delivery to deploy changes to fighter jets. SAP, my mental model of kind of a legacy system producer in many ways, are adopting continuous delivery and seeing dramatic improvement. Volvo Trucks, the New York Stock Exchange, Siemens Healthcare, all sorts of different organizations. Continuous delivery works for nearly every kind of software. Ericsson are using it globally to roll out their 5G networks to exchanges around the planet. So continuous delivery, I think, is the best way that we know at the moment of releasing better software faster. And I think it will have an impact on you whether you practice it or not. Either your organization will practice it and you'll need to learn the skills and the techniques and the approaches, or it won't. And one day, one of your competitors will show up and they will do it. And when they do, they will beat you in the marketplace, because this is a way of working more effectively. Thank you very much indeed. That's the end of my presentation. I probably have about 2 minutes for questions, but I'm certainly happy to take any questions for as long as we can.